Hello and welcome to misec Jackson. Today we've got Kent, also known as picat, and today's topic is the generative AI is a hot new topic, but how does it work? So I will go ahead and hand it off to you, Kent.
Awesome. Now, make sure Kyle has the slide or getting the slides together. Thank you now, Kyle. Awesome. So, hi, my name is Kent. I'm a product security engineer at HashiCorp, but I've been doing a lot of generative AI sort of explorations in my spare time. And I'm here to just kind of talk to you about some of those today. Specifically generative AI, building with generative AI and challenges with the current generation of large language models. So let's get into that. There's going to be a warning in the sense that I will not be covering all of the challenges that are involved with building with large language models or generative AI or AI. I'm going to be honing in on a very specific challenge, really, and the related challenges around that. But anyway, let's get into this. So generative AI. Generative AI is effectively, from a high-level concept, it's the subset of artificial intelligence, which it had machine learning, showing you this onion here. It can be used for generating text or music or other forms of art. And it uses basically algorithms to mimic human creativity at the end of the day. The specific types of generative AI that we're going to talk about today are large language models that probably definitely become a hot topic in recent months. They're an advanced AI system that are trained on extensive amounts of text in order to understand and then generate more human-like language. They excel in things like completion, summarization, translation. And at the very core, they take in input, they do some training on that to effectively give you this unit of compute, if you will, that allows you to reason about text. The one thing that I want to bring up, though, is that it's sort of like garbage in, garbage out at a high level. Biases in the input data will lead to skewed and unfair model outputs. Like ensuring diverse, balanced, and high quality data is vital to improve model performance and to promote responsible AI. And that cannot be overstated, frankly. And that'll be basically the only ethics that I will be getting into today as I sort of now transition to the engineering specifics here. I'm going to hone in squarely on OpenAI. Definitely, many people are using it right now. And I'm going to be talking about OpenAI's API directly. So this offers a way to use large language models to generate text. You can send a prompt to get from user input or whatever input you have, and then get high quality responses back for language-based tasks. So you can give it direction to go give you a meal plan, or given a list of things in your refrigerator, what can I make for dinner? These things it excels at. And it's a very simple API to use at the end of the day. And your application will be the one making these requests and getting a response from effectively this new type of cloud provider, this providing this new unit of compute, which is these large language models to reason about text and generate text. Other things generative AI can be used for, but we're just going to very much focus in on text today. So you send some JSON and you get some JSON backs, and we're just passing around some stuff. Now, you've definitely heard of ChatGPT, which is typically what people are thinking about when they're thinking about generative AI. And they're not thinking about the API directly, but I want to be clear that ChatGPT is effectively just using that API under the hood, and it's providing a wonderful consumer-grade wrapper to using these large language models in a way that's super easy to use. You don't need to make an API request without directly, when you can just have the nice application be able to make those API requests on your behalf, and manage all the problems that go along with that, which I'm going to expand upon. So your application is making requests and getting a response. What's really being passed around here is this thing that's being called a context window. Inside that context window, your request and response, you have these tokens. At an intuitive level, you can think of tokens as roughly equivalent to words. It's not exactly words, but these little bits of text. And this is what the model understands. This is the currency of large language models as they are today. These tokens, these little bits of word, are passed. You send it some and you get some back. So let's say we say hello. We're effectively putting some tokens in this context window. You can sort of think about the context window like a bucket where you're putting stuff in and being able to maybe take stuff out of it. So we put stuff in, the model gives us a response, and effectively it puts some tokens in the bucket. You continue along the conversation. Why you cats, or like what have you. You can do whatever you like here. It's just a small example. We're filling up this bucket. We're continuing to fill up the bucket by doing the request and getting the response. They continue to eat into this context window. And sort of what the question then naturally becomes at a certain level of conversation or certain scale of tokens, what do we do when we start reaching a potential limit here? Today, largely speaking, the limit is 4,096 tokens. There are versions of GPT-4 that allow you to have 32,000 tokens in a single context window. But today, we're just going to think about this 4,096 token limit. And this is the art of building with large language models, managing what goes in the bucket, what should fall out the bucket. And as your tasks naturally go beyond 4,096 tokens, whether that be generating new stories, generating new code, this stuff that the model doesn't know about, it generated net new information that isn't in its model of the world. And so as you don't want it to effectively hallucinate what's happening in your code base, you need to provide it with the proper context. And this is, again, the art of building with these things. So what do we do in this situation? At a very basic level, maybe those first two messages of hello and hello, how can I help you today? Maybe those, we don't need them in our context window. That's not really relevant to continuing this conversation, which was specifically about cats. Now, we still have some stuff in there. And again, your application actually needs to decide what to do about this. The OpenAI API is effectively totally stateless. Your application is always choosing what the context window contains. And so maybe we get rid of those two messages, but then we'll definitely lose the state of the conversation. So one very common way of handling this is by providing a summarization of these two messages. So we can distill this down. Those n number of tokens for the request and the response can be distilled down to maybe this conversation is just about cats. And that allows you to continue on the conversation without necessarily losing that previous bit of context. And this is useful for not just conversations about cats, but conversations literally about anything. Now, all that past history, though, let's say it was like net new code, so new lines of code, new functions. Your application isn't going to try to forget that information if it's trying to provide this long-form conversation around the code base. So it's going to have to keep this history, these new tokens that were generated, and do something with it. So what do we even want to do with that? We want to look through the previous messages that have happened to identify relevant context in the conversation. For example, if I had a conversation about ketchup and then dogs and then cats, and I transitioned the conversation back to ketchup, maybe I said to the model, I hate ketchup or something along these lines. I would want the model to maybe have that context, depending on my application's use case, of course. But I may want it to have that context. So when it gives me a response about ketchup, it's not telling me how great ketchup is, because that wouldn't be a great user experience. Now, this scales to other tasks, but we can think about these messages, effectively these requests and response, pairs that make up these logical threads in the history of the conversation. Now, we're going to want to search. Our application is going to want to search over these messages. So we can use our classic sort of ranking algorithms like best match 25, which is typically used by things like Elasticsearch. And we can also do more, let's say, new age searching techniques, typically coined as neural search. So cosine similarity, which I'm going to get into in a second. So what do I mean? So like in searching these messages, so let's say we're just at not even hit a thread of logical messages that are connected. Like let's say we just had kind of more dispersed documents that exist. Maybe you're ingesting information from a company. You have their PDFs, or you're trying to ingest all this various information, trying to find relations that exist in these texts that you can feed as context based on the based on the strings that are provided by the user. So we want to be able to find interesting similarities. Like, for example, whales are likely fairly similar to dolphins in a sense. And maybe whales are more similar to dolphins than they are to cats or they are to birds. we would want some mechanism to be able to search over messages or search over documents to be able to extract relevant bits of context. So this is where embeddings come into play. So these are compact, high-dimensional representations that take, let's say, strings of text and turns these strings of text of arbitrary length into these fixed length floating point numbers. And each floating point number intuitively is a dimension of the n-dimensional vector. So if we had a vector of 3 floating point numbers, that would be a 3-dimensional vector in theory, in practice. And in the case of OpenAI, they have an embeddings endpoint that we can use that takes in strings and provides us these floating point numbers. And it's specifically something like, I think on around like 1,500 dimensions, something along those lines, but in the scale of like 1,000. So we can take these and we can do really interesting things with these embedding representations that effectively you can think about as like these points in space that represent a thing, a piece of text that we can do linear algebra on top of to identify how things are similar or not. So is like one example of how we can take embeddings and start taking these n-dimensional things, let's say 1,000 plus dimensions. I can't visualize what 1,000 plus dimensions really looks like in my head. I can visualize 2D and 3D space fairly well. And so we can use techniques to actually take these higher dimensional data and to reduce this down to things that are much easier for us to interpret, specifically 2D and 3D space, right? So we can take these n-dimensional vectors and take it down to just 2 dimensions. And as effectively one of the de facto examples of TNSC, specifically TNSC is T-distribution, stochastic neighbor embedding, and PCA is principal component analysis. And these are just methods that allow you to take these higher dimensional things and reduce it down. We can see on the far right here, this example of using the MNIST dataset for handwritten numbers. And this is very commonly shown for TNSC specifically. We can see that all these little groupings are effectively just these ones or twos or threes or four. These are the actual numbers themselves clustering themselves together using this TNSC technique, which allows you to understand or maybe get a little bit of a glimpse into what the model or your application is thinking, how things are related as they are spatially here. So more specifically, outside of understanding how they are related spatially with TNSC, just for like visualization purposes, we can provide, we have other means of using linear algebra to find interesting similarities between, let's say, vector A or vector 1 and vector 2. And we use cosine similarity. And this has effectively become like the de facto way everyone is doing similarity search on top of embeddings right now. It provides the similarity measure between two non-zero vectors. And I provide the basic like math intuition and a little bit of Python code to show what the nuts and bolts of cosine similarity is. But from an intuition perspective, on that right-hand side, you can see these 2 points. And we can see the cosine angle between them that gives us a value effectively between 0 and 1 that tells us how similar vector 1 and vector 2 are. From an intuition perspective, if it's 0.8 or greater, they're likely fairly similar. Now, again, all that allows us to do is take these list of floating point numbers, vector 1 and vector 2, and then allow us to compare them to obtain a single floating point number, the similarity, the measure how similar these two things are, which allows us to do interesting things like this, where we can compare whales and dolphins. We can get the embedding for those strings, both whales and dolphins. And just for the visual representation here, we can show how they are in 2D space. And then we can get the cosine similarity, which is, again, this value between 0 and 1. And in this case, it's 0.9 whatever. Now, if we were to take dolphins and replace that with cats, obviously we'd have a different embedding, and when we would get a different similarity metric. And it kind of makes sense that whales are more similar to dolphins than they are to cats. And again, this is sort of appearing into the way that your application would be thinking about these strings as it's choosing which strings to include in that context window. This is a technique that everyone is employing to enable long-term memory for large language models, because effectively the context window is the working memory. If it's not in there, it might not know about it, especially if it's not in the model of its world. All net new stories or code, etc., it will not know. So you need to sort of garden this context window and make it useful for your specific task. So we have this history, and this history can be made more useful in the sense that we can search it very effectively using this concept of neural search with cosine similarity. And we can use OpenAI, again, to get these embeddings. So we don't even have to go build our own embedding thing if we don't want to, which you can go use off-the-shelf ones, et cetera. But specifically, we can use OpenAI, and we can get these embeddings for each message. So whether it's the user's text or it's the model's text, we can then use these to be able to search for the current user input. Well, what's similar? So again, catch-up, being able to search past previous messages for the concept of catch-up. And then maybe summarize that down and put that in the context window. And indeed, we're going to probably want to store these embeddings in this history in some sort of place, on disk, in a database, what have you. There are, and then we can do cosine similarity on top of that to, again, really curate this context window. There are purpose-built storage mechanisms that have this cosine searching and querying and all this good stuff inside of it. This is becoming a huge class of new databases, these vector databases. And of course, existing databases, whether it be Redis, whether it be Postgres, they have the ability to handle these new, these vector search capabilities using plugins to extend their existing functionality, because they are just storing floating point numbers, really, and then doing just a little bit of math on top of those floating point numbers, like very much just a little bit of math. And what we're trying to do with this context window is we're trying to effectively spill these buckets intelligently into one another so that we can accomplish our task, get some results at the end of the day. And we're going to effectively be pulling out the concepts of the world that OpenAI's models know about in the context of what we can provide it, and trying to effectively pull out these net new tokens from this thing, generating net new information. And we, as callers of the API, builders on top of these APIs, whether it be OpenAI, whether it be Anthropic, whether it be Google Vertex AI, etc., all of these present a similar context window problem. And this is the foundational problem that you need to handle when you're building on top of large language models right now. So again, your application is just calling OpenAI and getting responses and playing this juggling act back and forth, choosing what to put in the history, choosing what to summarize. And your application needs to handle that, which you would typically get for free if you're just using ChatGPT right now. Now, your application is probably going to get user input, whether it be from yourself or users that is paying to use your application. But there's other weird things that we can do here. Specifically, we could turn the model around on itself, and we could have it have a conversation with itself to effectively do this concept of reflection. So let's say it generated this Python code, and this Python code used functions that did not actually exist in libraries that are available in Python. The model, you can ask it to reflect on the response that it gave. And in many cases, it can fix its own hallucinations. Not always, to be clear, but using a strategy of like reflecting on yourself 1 to 2 times can improve model and results from the actual the text that you get from the models themselves. And this is a little weird, again, pointing the models on themselves, but this is a very powerful technique that can be used in interesting ways. So the basics is just 1-to-1, the concept of reflection. We have the ability to wire together these generative models that understand human language and, of course, generate this human language to have full weird conversations with themselves about a topic potentially seeded from a user. The user maybe gives it some sort of instructions and had built in your application was built in a way that used the generative AI capabilities in a specific way. It's not just doing 1-to-1, but behind the scenes of the single interface that the user is using, there can be many more model calls behind the scenes. For example, if we were to ask the model or this application that's using these models specifically to build a game of Snake for the browser, we could have, if we chose to build our application this way, one aspect, with the first top being effectively maybe the manager. And it says, to build a game, you do X, Y, and Z. Is providing information with that user to the result that they're trying to accomplish. Specifically, this bit of code here. It could choose to split up these pieces of work into tasks that could be delegated to specific models that are specifically chosen to generate code or to review code or to do security review on code. You can wire together these generative AI capabilities in like actually bizarre ways. Tiny little companies like a weird version of The Sims that can accomplish interesting results as long as and if your application can intelligently flow these tokens into the appropriate buckets. So that's where my presentation ends today. It's definitely not the end of large language models or generative AI. And this is the current generation of large language models and of just really, I think, AI in general. There are a lot of things to explore in the future, and I recommend you do explore them. And with that, if anyone has any questions or whatnot, we can take it to that. But thank you very much. I imagine Kyle's there.
Okay.
Oh, there we go. Now I'm on camera.
Hello.
All right. Hi, Kent. This is Isaac.
Hi, Isaac.
So I dabbled a little bit with machine learning stuff over the last year, learning classical machine learning models and sort of the basics of these things. I went through a book called Practical Deep Learning. It was a Python book, and it went through a lot of the classical models and stuff like principal component analysis and whatnot.
Yeah.
It strikes me that this is maybe dumb, and there might be better ways to get into modern, useful AI, machine learning, this space. But in what way would you recommend new people interested in this stuff hop into things?
I think, to be clear, looking at the foundations of like classical machine learning, if you will, is super, super relevant, even in today's large language models. I think the main thing that you sort of need to decide is whether or not you want to be a builder of machine learning, like understanding how neural networks are built, or building on top of this, again, this new unit of compute that is provided by these new sort of large language model cloud providers like OpenAI or Google or Anthropic, etc. This is more of the question, I think, of like where should people get into it? Because if you're looking to get advantages out of the current generation of large language models, like frankly, like these APIs are available and incredibly powerful. If you're looking to do more on-prem use cases that would maybe never even allow this API call to be made, well, then it's super relevant to be looking at all of that classical stuff. What you really, I believe, want to be looking at and learning more about at this point is specifically how transformers work if you're looking to apply large language models, which some more classical machine learning stuff won't really cover or will cover loosely because it's, relatively speaking, one of the newer things that exist, especially in this case of generative AI. But it is a really interesting architecture to look into. I also highly recommend, for whatever this is worth, and this is a little bit more tangential, but looking at Jeffrey Hinton's paper on the forward algorithm. Highly recommend reading that paper for whatever that's worth.
Thank you so much. Yeah.
No problem.
Figure out what you want to do and go from there, it sounds like.
Exactly.
Mm-hmm.
All right. Any other questions? What's that?
That's enough for the live stream.
Okay. All right. So thank you very much, Kent, for your time. Thank you for the wonderful talk on AI. And we will hopefully see you next time.
Of course. Thanks for having me.
When's the social?
Oh, and the social for misec Jackson will be on, let me get the exact date. It's the 4th Thursday, right? Last Tuesday. So May 30th will be the Jackson social. And then in case you have not seen the news, MisecCon is in November 17th, right? In Lansing. So there's more to come on that. The website is up, and that is at misecon.misec.us. And keep your eyes peeled there, and there will be more information as it comes out. So Until next time, have a good one.